So here you can see some fast-acting doors. There are safety issues with any design, but these are highly efficient doors that, if used properly, people are trained to properly use them. They have built-in safety features. They're not going to squish somebody. Air curtains, where it's literally blowing air instead of using large sheets of flexible plastic, little plastic fingers that are going down to keep the air movement, or in combination. An air curtain, maybe you've seen these in, I don't know, Jack in the Box in LA or something. I know I've seen them at numerous places where it's hotter weather. You walk in the door and all of a sudden you get this blast of air. What are they trying to do? They're creating a curtain where the cold air stays inside, the cool air conditioned air, and this blast of air going down is a shield that keeps the warm air outside. A vestibule is a structure where you basically have an intermediate space. So you go in through one door into the vestibule, that door closes, then another door opens and you move in. They can be very efficient, but they also put a buffer zone where the total loss of heat is much, much less. Water vapor transmission, extremely crucial. The building envelope must prevent water vapor migration from the outside to the inside. And that happens. So you need vapor protection, vapor barriers built into the walls and ceiling. Failure to prevent water vapor migration results in increased energy cost, diminished insulating effect, structural damage, biological growth, that's a huge food safety problem, and ice formation. And so you have different types of vapor retarder materials. I'm not going to go into the details, but it's essentially basically saran wrapping your building in every way possible so there's no leaks where vapor can get inside. And if you look carefully at these photos, you can see where there have been problems and damage due to icing and a lack of proper vapor barrier structures in the building. Not sure what that was doing. Anyway, walls and ceiling insulation, I think that's pretty obvious that they need to be insulated, but they also need to avoid trapping moisture inside the walls. That can be another really bad problem. You get icing in the walls, the ice will damage the insulation, damage the walls, and become a microbiology hazard that can do further damage to the building or be a food safety hazard in your facility. Cool roofs. This is just looking at different colored materials that you have. This darker material at 173 degrees Fahrenheit. That's cooking temperature, that's sterilizing temperature. With a cool coating, it brings that down by 65 degrees roughly. That's a huge reduction in temperature out in the hot sun of the same material. And there are materials that are more high-tech that can even do more than this. But this is a 90-degree or 89-degree day in Sacramento, California. So, in a hot, sunny day, which isn't incredibly hot, but that's still just a normal summer day in Sacramento. And there's lots and lots of different ways to think about materials and colors that will help with roof insulation and reducing overall heat absorption and temperature. You can also add solar to the roof. So, hey, the solar is going to be absorbing the energy from the sun. And so the energy never reaches the roof. The roof is in shade because it's covered in panels, and these panels are generating electricity, another way to solve the problem. Or another ingredient to all of the tools you have to solve these problems. During loading and unloading of refrigerated trucks, you need to be looking at how does that truck back up to the refrigerated warehouse? How does it properly seal? So you can provide extended overhanging roof to shade the truck, reducing its solar load. You can do other things as well. I won't get into the detail there. In the refrigeration system itself, energy is required for refrigeration, or energy required for refrigeration constitutes the major cost of operating a refrigerated storage facility. No big surprise. Your number one expense is the energy of refrigerating that warehouse. Energy efficient refrigeration technologies and operating strategies, efficient piping design to minimize the delta P, which is the change scratch that. Can't think of the word. Anyway, use high efficiency motors and variable speed drives, compressors, evaporator, and condenser fans, fluid pumps. Those are the types of terminology I want you to know. You should know compressors, evaporators, condensers, and expansion valves. Now, we haven't talked about fluid pumps, but in a large system, you need more than just a compressor in many cases to be driving things around. You might need additional pumping in some situations. So natural refrigerants, the anhydrous ammonia, also known in the refrigeration world as R717. It is not an ozone depleter, and it is not a global warming potential chemical. It has some great advantages. It's efficient as well. It just is dangerous for certain applications because if there's a leak, the pure ammonia vapors, if it's anhydrous ammonia, which is the one used for refrigeration, ammonia vapors in that state are dangerous. Carbon dioxide, R744. It has no ozone depletion potential and negligible global warming potential. Again, carbon dioxide is a significant gas for global warming, but when used as a refrigerant, it's negligible. We're not talking about generating huge amounts of it. And then ammonia, carbon dioxide cascade systems. Don't worry about the details, but these are some of the natural refrigerants. I'm not going to get into load calculations. You can pause here and read some of this, but it's basically understanding your microclimate, your walls, the roof and colors and wind and what's going into it, all kinds of things that we've already discussed. Energy use and facility management. You need